let's use conservation of angular momentum to consider the behavior of these flywheels. We have a flywheel rotating without friction at an angular velocity initially of 600 revolutions per minute on a frictionless vertical shaft. We'll call this our initial situation. And we have, let's call this my z direction. And then it's lowered, and a second flywheel, which is at rest, has a moment of inertia 3 times the initial, comes into contact, and then there's friction between them. So we have energy dissipated due to the friction between these two things. And then at the end, they have the same spin as they come into contact and end up with the same velocity at the end, the same angular velocity. We want to know what's that angular velocity of the combination. Let's see if we can do this. We'll use conservation of angular momentum. That says that my initial momentum is equal to my final momentum, assuming we can neglect external torques. There is torque exerted here, but it's between these two. There's that friction between them, but that's internal to our system. We're considering both of these as our system, so there's no net external torque. Initially, we have just the top flywheel spinning, or actually no, initially it's just the bottom flywheel spinning, it looks like, with I naught as our angular momentum, I naught omega naught. And then finally, the combination of those moments of inertia are combined. So we have that initial I naught moment of inertia plus the 3 I naught moment of inertia of the top wheel times our final angular velocity. We can solve for our final angular velocity in terms of our initial stuff by dividing both sides by this 4I naught. This gives us omega final is equal to omega initial times I naught over 4I naught. The I naughts cancel, and we're left with it's just a quarter of our omega naught, which is 600 revolutions per minute divided by 4, or 150 revolutions per minute. If you're fine with those units, that's fine. If you wanted it in radians per second, you can convert and call it 15.7 or 15.7 radians per second. Let's consider part B. What fraction of the initial kinetic energy is lost in this coupling? Here, we have to calculate our rotational kinetic energy. We'll say that initially and finally, we have different rotational kinetic energy, and we expect that we've lost some energy to friction, that it's changed from mechanical energy into heat via friction. Initially, we had 1/2 I naught omega naught squared. And then finally, we have 1/2 4I naught times omega final squared. And we just found what omega final was. So we can say 4 divided by 2 is 2. So this is 2I naught times 1/4 omega naught squared. We can simplify this a little bit more and write this as my final kinetic energy is 1/8, because 1/4 squared is 1/16. 2 divided by 16 is 1/8. I naught times omega naught squared. And now we can compare these and say what fraction of our initial kinetic energy is lost? Well, the fraction that's lost is related to this ratio. So we can say that initially we had 1/2 I naught omega naught squared. Finally, we have 1/8 I naught omega naught squared. So it looks like we've lost 3/4 of our initial energy. And we can show that by calculating something like my final over my initial will be 1/8 I naught omega naught squared over 1/2 I naught omega naught squared. Those things all cancel, and we're left with 1/4, because 1/8 divided by 1/2 is the same as multiplying by 2, so you end up with 1/4. And that says that we have at the end 1/4 of the energy we started with, which means that we have to have lost 3/4 of our initial energy. And where did that go? It went to friction as they collided and slowed each other down, or one actually sped the other up. The stationary one slowed the other one down. It went to that friction.